Okay, welcome back everybody to Chemistry 2341, Organic Chemistry 1 here at Texas State University. I am going to continue on with Chapter 9. This is where we were talking about NMR spectroscopy, and then we're going to go into a second type of NMR spectroscopy and another cool kind of spectroscopy technique we can use to figure out the mass of things. So what I'm going to do now is go ahead and do my administration thing. So administration wise, we have our homework for Module 9 is due on Monday at midnight, Monday the 16th at midnight. So you have that extra week time over the weekend to finish those up. We will have an activity on Friday the 13th now, and I will email everybody out after this class, and I will have that activity uploaded to Canvas and emailed to you by Friday morning so that we can start doing that. And it's all about NMR, how many peaks something should have, where they should be kind of on shift wise, and then look at a couple NMRs and try to go, ooh, which compound could it be just based on the NMR? So it's just going to be a few little simple questions to really solidify the topic for you and get you kind of thinking about, ooh, that's what it all means. So that's kind of what we're looking at there. Okay. Looking ahead, Module 10, which is free radicals, will begin on Monday the 16th. And so we'll talk a little bit about that. And then we should actually get maybe a little ahead and jump into Module 11, which is alcohols, by the end of that week. So count on at least 2 lectures for the radicals and then maybe a start on Module 11. So because we do have that short week on the week of November 23rd because of Thanksgiving. And so technically we do have class Monday and Wednesday. Of course, some of you might travel, and that's okay because we record the lecture and you can look at it on your own time. As long as you're caught up by Monday, you should be fine. Okay. So because that homework will be due on Monday, November 30th. Okay. Any questions about administration at this time? What's the second Friday? Yeah, it is the second Friday the 13th this year, and I hope it kind of undoes whatever happened to us before. So maybe it'll act as a reset, like shaking your Etch-a-Sketch, if you know what one of those is. Anyway, so that's a good point there.
Maybe they'll cancel each other out. Who knows?
Yeah.
I did have a quick announcement about SI, which was that it's still going on. My sessions are still a thing. Yesterday's session was a little low in attendance. So I just want to remind everybody that you are more than welcome to continue going to sessions. You don't even really have to stick to a particular session anymore. If you're available and you want some reviewing on some material, feel free to join. I suggest putting all my sessions on your calendar and then just, going to whichever one you're available in the week. But yeah, just to, friendly reminder, sessions still exist. I still have a lot of good stuff planned for y'all. So if you have any questions, feel free to shoot me an email. But yeah, let's get started with the lecture.
Yeah, and the next 2 modules, modules 10 and 11, have some really new chemistry. So going to the SI session and getting to really sink in before the final would be a really good idea. Okay. Okay, so let me go ahead and share my screen, get me back onto our, oops, let me get back to the right table here. All right, so what we were talking about on Monday is we talked about NMR and what it was, and the fact that we were doing, the first kind of NMR we were doing is what we call Proton Nmr, which is all about the hydrogens, right? And the fact that hydrogen's major isotope has 1 proton and no neutrons, and so it has spin. And we can look at this spin using radio waves and a big magnetic field. Okay, so having that magnetic field and having the radio waves pulse it into that field to knock things in and be aligned with and not aligned with that magnetic field is what gives rise to our signals. Okay, so when we talk about our different things that are important for our NMR signals, we said that in Proton Nmr, we have 4 things that are important. The number of signals we have, and that's associated with the different kinds of hydrogens we have. The intensity of those signals. And again, that's not the height of the peak, It's the integration under the peak. Because as we start doing spin-spin splitting, we'll see the peak start spreading out and the heights will come down, but the total area under the curve will equal the number of hydrogens associated with that shift. And then of course, the third thing is our shift. And we talked about all those last time. Go review the video if you haven't, if you didn't see that before. But today we're going to talk about number 4, that spin-spin splitting, and the 3 rules associated with spin-spin splitting. Okay, so we talked about upfield, downfield, and that gave us what we have. And so the more electronegative an atom is, or the more double bonds we have, or an aromatic ring, it keeps shifting us further and further away from our standard TMS. Okay, now we have to figure out how many hydrogens are within 3 bonds of those equivalent protons we're talking about. Remember, those equivalent protons are the ones that give us the position, our shift, our number of signals. And so now that we have a signal there, we have to figure out how many peaks we're going to see for that signal. And that's all about these 3 splitting rules. Okay, so equivalent protons do not split each other, meaning that if you have 2 hydrogens on the same carbon and they are equivalent, like not in a ring, sometimes the ring makes them non-equivalent. If it's like a straight chain hydrocarbon and they're on the same carbon, they are typically equivalent protons. Now, we also can have 2 hydrogens on the same carbon that aren't equivalent in things like alkenes. So we have to watch out for alkenes and rings when we're talking about equivalency, because when we have, when we have an alkene here, even though these hydrogens over here are on the same carbon, they are not equivalent because of their through space interaction and their distance away from that chlorine right there. So we actually end up having 3 signals there. So we have 3 non-equivalent protons. Okay, so let's not forget about equivalent protons and what they are. So equivalent protons do not split each other, okay? So all of the other non-equivalent protons that are within 3 bonds of these hydrogens will split that peak. Okay, so these equivalent protons give rise to a peak, and we call that would be the number 1 in this n+1 rule. Okay, so that's the peak of non-equivalent protons, of equivalent protons. And then the n is all the hydrogens we can see within 3 bonds of those hydrogens. So if you had a methyl group here and a methyl group here, you end up having a total of 6 hydrogens within 3 bonds of this peak we're talking about. So n is the number of non-equivalent hydrogens within 3 bonds. Okay, so we always get 1 for our hydrogen, our peak we're talking about, and then the n is all the other hydrogens within 3 peaks. Okay. And therefore, we need to have that rule. And so we'll see 1 peak split into 2 peaks, 3 peaks, 4 peaks, sometimes 20 peaks. Depends on how many hydrogens you have within 3 bonds. Okay. The third rule is splitting is observed for non-equivalent protons on the same or adjacent carbon. So in the case of our cyclopropane with a chlorine here, we had hydrogen here and a hydrogen here and a hydrogen here and a hydrogen down here, right? And we saw that these 2 hydrogens were equivalent and these 2 hydrogens are equivalent because of their position on the ring, which means this hydrogen is going to split this hydrogen because they are non-equivalent. So in this case here, we're talking about a hydrogen within 2 bonds of a non-equivalent hydrogen. So the true rule is that any hydrogen, non-equivalent hydrogen, with 2 to 3 bonds away will split your single equivalent proton peak. Okay, so let's apply that and look at that a little deeper. Okay, so the first rule kind of is that, you know, the equivalent hydrogens don't split each other because they have the same magnetic field applied to them and they have the same number of up and down spins because they're equivalent. However, if you have a hydrogen on 1 carbon and it's in the magnetic field here, the hydrogen on the adjacent carbon is in the magnetic field as well, but if it is spun anti-parallel to that, that changes, that gives a difference in the magnetic field, and that hydrogen can sense that. And so some of them are going to be anti-parallel and some of them are going to be with parallel. What that means is the ones with parallel are going to add to that peak, creating them, shifting them downfield slightly, and therefore the ones that are against the thing are going to shift it downfield, upfield slightly, which means your single peak is going to turn into two peaks, one going upfield and one going downfield from that original signal. Okay, so if they were equivalent, then those magnetic fields would overlap and align and cancel each other out, and we don't see any splitting. However, because they are different, one shifts it slightly up, one shifts it slightly down, and we get our splitting. So in this case here, we have this hydrogen here, which is the A hydrogen, is chemically non-equivalent to this B hydrogen. Therefore, the A hydrogen is our signal, and our B hydrogen is the N. So our N+1 rule here equals, we have one hydrogen in N, one is for our signal, and so we're going to end up with two peaks. And so that gives us our doublet. Okay, so in this case, we can only get a doublet for that peak. And likewise, this blue signal right here is going to give us one peak for that. And this is the only hydrogen within 3 bonds. So that's our N number, and it's also 1, is equal to 2. So that means this B hydrogen peak is going to give us a doublet. This A hydrogen peak is going to give it a doublet. But if they were chemically equivalent, we wouldn't see this shifting of slight upfield and slight downfield, an equal amount, and we would have a single peak. Okay, so now let's talk about the next rules here, rules 2 and 3. All right. So in rule 2 and 3, rule 2, of course, is N+1, and rule 3 is the hydrogens that are, if they're non-equivalent in this hooked to the same carbon, they can still split. So let's look at that in this particular case right here. So in this particular case here, we have one hydrogen here, our A hydrogen, and then we have what we call a B hydrogen, and we need to see if this second hydrogen is magnetically equivalent or not. So we're going to have this one, we're going to call that hydrogen B prime, just to see. Okay, so what we'll look at here is that A right here gets a signal, so that's 1. And then we have 1, 2 hydrogens that are within 3 bonds. So that means we have 2 plus 1 is equal to 3. Okay, so why are we getting 3 peaks here? Well, because we have 2 things that are splitting that single ping. One is splitting it upfield a little, and one of them splitting downfield a little. The other one's doing the exact same thing. And so the two upfield peak the 2 upfield peaks go together, the 2 downfield peaks go together. And it turns out one upfield peak and one downfield peak overlap. So we end up getting those 2 being in the same position. And that's why we have, this is our 1 for just shifting downfield. This is our 1 for shifting an upfield from one hydrogen and an upfield from one hydrogen and a downfield from the other hydrogen. And then this is downfield from the other hydrogen. So what we end up with is one shifting it further up, one shifting it further down, and the other 2 kind of canceling each other out, but giving us an intense signal. And so the intensity of the signal is 1 to 1 in relative intensity. But if we integrate it under the curve, we actually see the entire area under the curve is a value of 1. That's where that integration under the curve is more important than the height of the peak. Okay, so let's look at the other 2. Okay, so the other 2, because they're magnetically equivalent, and they are right next to each other, we can say that they are not going to split each other because they have the exact same environment around them. See, because we don't have a ring making one above and below the plane. We have the same bonds on either side. So they are magnetically equivalent. So that means we get one peak for just those peaks right here. And we only have one hydrogen within that three bonds, 1 + 1, which means we should get a signal of two peaks. Okay, so that B hydrogen peak is going to be split, half of it upfield, half of it downfield, to give us a doublet. But we have a total of two hydrogens here. So that when we look at the integration of that peak here, we see the area under the curve is 2. Okay, so do we see why things are starting to split? Okay, so you can imagine one way to look at it is if you have one signal and it's split by two different hydrogens, so you have one signal that's split, and then each one of these splits again, and then when they overlap, that gives you a total of 3 peaks. Okay, so this is a really cool concept in the fact that you have one hydrogen splitting it in this way, then this was splitting it upfield and downfield, and then this is splitting upfield and downfield again. So we get that total of 1, 2, 1. Okay, so what we're going to see is in the common patterns, we're going to have a specific intensity, and we're going to have a specific number of peaks associated with that. But all we really need to do is make sure we follow the n+1 rule. The n+1 rule will tell us how many peaks with it, and the peaks always follow that same intensity gradient. Okay, let me tell you about that intensity pattern. So when we have no hydrogen splitting our signal, we only have one peak. So our n is equal to 0, we have one peak, and its intensity, relative intensity, is 1. Okay, that's not the integration. That's just if we looked at the size of the peak. Okay, so the height of the peak, if you can imagine. Okay, now if we had a one peak that was then split by one hydrogen, that's going to go half of it upfield, half of it downfield, and we're going to get 2 peaks. Okay, and they're going to be split equally. Okay, so that's how we get that second thing called a doublet. Okay, so we have a singlet, a doublet. So now if we have 2 hydrogens, one of them is going to split it upfield and downfield, and then they're going to be split upfield and downfield again, giving us a total of 3 peaks with an intensity of 1, 2, 1. But again, that's the intensity of the peak, that's the height of the peak, not the area under the curve. With 3, we're going to end up with 4 peaks, which gives us a quartet. If we have 4 hydrogens adjacent to it, we get 5 peaks, quintet. 6, 7, 8 goes a sextet, septet, octet, non-tep. Okay, now look at the relative intensities here. By the time you get to something like a non-tep here, you have an relative intensity in the middle of 70, and these outside peaks are a relative intensity of 1. So they're going to be really, really small. So you're going to have this really cool pyramid looking shape. Okay, so let's take a look at what that kind of looks like. Okay, so let's apply all those rules. Let's figure out non-equivalent protons. Let's figure out our n+1 rule and figure out if things bonded to the same carbon are magnetically equivalent or not. Okay, so let's look at propane. All right, so propane, 3 carbons. We have, let's see, we have 6, 7, 8 hydrogens. We have no double bonds. So that gives us a starting point. Okay, so if we look at these, the first set of hydrogens here on this first carbon here, we have 3 hydrogens bonded to a carbon and then bonded to a carbon. Okay, all right, that's a good starting point. If we look at these on the other side right here, we have 3 hydrogens bonded to a carbon, bonded to a carbon. Okay, they look chemically equivalent. Now, because they seem to be chemically equivalent, we're also going to assume that they are magnetically equivalent as well. They have the same deshielding and shielding because they are chemically the same. Okay, now we know the middle ones can't be the same because that carbon only has 2 hydrogens on it. Therefore, we now have a different structure, so they must be magnetically different than the other 2. So we're going to call those different, And we're going to say that these two hydrogens here are magnetically different. Okay, so just based on that, if we look to where we expect the peaks to be by shift, remember, TMS is our 0. The most like a long chain hydrocarbon, the most like methane, the closer it's going to be to propane, the closer it's going to be to that TMS, that 0 point, which means these methyl groups are going to be closer to 0 than this CH2 group. Okay, just because they are closer to methane, which would be the closest to 0. Okay, and just by taking those two hydrogens away, we do see that chemical shift. And if we took one more of those hydrogens away, we would shift up again. Okay, so those number of hydrogens can show us a lot in that down in this little small downfield area. Okay, now let's talk about our splitting. Okay, so if we look at these hydrogens, we got 3 of those, but they're equivalent to these 3 hydrogens over here, which means we have a total of 6 hydrogens, but they're magnetically equivalent. So that gives us 1 signal. Okay, so that's our 1 in our N+1, and then it has 1, 2 hydrogens adjacent. So our N in this case is 2, which means we're going to get a total of 3 peaks for all of these hydrogens. Okay, so if we were going to predict that, we would say, okay, those hydrogens are closest to methane, so they're going to be closest to 0. We have a total of 1, 2, 3, 4, 5, 6 hydrogens. So our integration is going to be 6 hydrogens. And it has 2 hydrogens that are split, so it's going to give us a triplet. And our relative intensity on the triplet is going to be 1, 2, 1. All right, does everybody follow that? Okay, so we haven't broken any rules. We've used all those rules, all 3 rules, okay? We don't have a ring, so we really don't have to worry about number 3. Okay, so now let's go backwards and do the other one. Okay, so what I'm going to do is I'm going to erase that. And now that we know that all of these hydrogens are the same, that the 6 hydrogens here and here are the same, we know that's going to have to be used in our N+1 calculation. All right, so let's think about these 2 hydrogens here. Okay, those 2 hydrogens there, they're going to be shifted further downfield from the TMS because it only has 2 hydrogens on it. Okay, and those 2 hydrogens are magnetically equivalent, so they give 1 signal. Okay, now let's do the N+1 rule. We have 1, 2, 3, 4, 5, 6. Our N in this case is 6. So we have 6 plus 1 is equal to 7. So we should see 7 peaks for those 2 hydrogens. Okay, so what we see here is that look, 1, 2, 3, 4, 5, 6, 7. And our relative intensity, our one in the middle is the highest, then it kind of comes down, and then these little peaks at the end, those are those relative intensity of 1. Okay. But if we integrate under that curve, we're going to see that we have a total of 2 hydrogens. Okay, and the relative ratio here is 20, 15, 6, and 1. So, and we can use that, find that from the previous table. Now, the absolute number of these is not as important as the number of peaks, and you'll see certain patterns. It'll have a visual pattern associated with it, and I'll show you that in a minute. Okay, so do we see how to apply the individual peak, the shift, and the intensity, plus the splitting to give us an indication of different parts of the molecule, and we can start to see where things are connected because of that. Those hydrogens had to be within 3 bonds to make that split, so we know that they have to be connected very close together. So now we can start linking fragments together. Remember, with IR, we only saw different types of bonds. We couldn't really link them together. In Proton Nmr, we're starting to link them together to give us actual chemical structures. So that's the cool part there. All right, let me show you some typical patterns. Okay, some of the more common patterns are things where you have 1 hydrogen on each carbon and they only split each other once. So this hydrogen is going to give you a doublet, and this hydrogen is going to give you a doublet. So one signal, our N is 1, so we end up with doublets. Okay, so let's add a hydrogen to this, left side here. And so we still have equivalent hydrogens, and they're only being split by the one hydrogen here, so we still get a doublet. But this hydrogen now has 2 hydrogens splitting it, so we get our nice triplet. And again, it's a 2, 1, 2. So it's a nice even. And notice that where it's centered here, notice this is centered. These are split either side of this center peak. This is now back to the exact center of that system. And we can see that going back and forth. Now let's add another hydrogen here. That's going to make this side split to 3 because we have equivalent plus 2. This side is still 3 because we have equivalent plus 2. Okay, so let's change it up a bit. Let's go ahead and add a third hydrogen to the left side, but take away one of the hydrogens on the other side. And look at that pattern here. So what we'll see in this pattern is we have a total of 3 hydrogens here that are going to split this one. So to give us 4 peaks, it's giving us a quartet. Okay, but these 3 hydrogens are magnetically equivalent. And so it is going to only split it once, giving us our doublet. Okay, do you see how by recognizing this pattern, you can start to pick up, oh, there must be 2 hydrogens nearby. There must be 3 hydrogens nearby. And then you can help to identify these fairly quickly just by looking at the types of peaks you're getting. Let's add another hydrogen here. And when we do so, we end up with our, this being split by our N now is 2 on the left side, giving us rise to a triplet. But our N on the right side is now 3, giving us rise to our quartet. Okay, now let's split up some stuff and try to see if we can't get a more complex thing. Let's add a methyl group. Now this methyl group is chemically equivalent to this methyl group because they have 3 hydrogens each. They're both bonded to the same carbon. So they are magnetically and chemically equivalent. And so they would give rise to a single peak. And there's only 1 hydrogen within 3 bonds of these. So it's going to be split into a doublet. But note the relative intensity of this is going to be 6 hydrogens, but it's still only a doublet. Okay. So our N on this side is now 6. Our N is equal to 6 because we have 6 of these hydrogens here, splitting this 1 peak, giving us rise to a 7, a heptet. So we look here, 1, 2, 3, 4, 5, 6, 7. Yeah, we have 7 peaks there. Okay. So that's showing us that we can follow all these rules and look for these patterns. And so you'll see that this also integrates to 1 hydrogen. So by adding number of splits to the integration, it'll help you identify which segment of the compound you have. And then let's just go crazy and take away all the hydrogens in that methyl group all by itself. It's got no splitting nuclei. It's a singlet back. It's back to a singlet again. Okay. Do we start to see that pattern? Anybody see that pattern? Okay. So when we go with our activity on Friday, we're going to do a little bit of this and give you a little more confidence in the splitting patterns here. All right. So that works really well for straight chains and rings and stuff. However, benzene tends to be a little more muddled because that, number one, they're shifted way downfield in the 7 to 8 range. And the equivalency of the hydrogens is, they might be equivalent, they're not. So I want to show you some common patterns we see in benzene rings that we might not see in those straight chain hydrocarbons. So for benzene, if we just had benzene by itself, it gives us a singlet because they are magnetically equivalent and they are chemically equivalent because there's nothing breaking up our conjugation or changing any kind of partial charges or anything like that. So you get a single peak. However, if you do a substitution, and this substitution is a non-polar bond, right? So it really doesn't, it's not electron donating, it's not electron drawing. So it has a small effect on the splitting of those hydrogens. They're almost equivalent, but not quite. And so we see a typical pattern where we have this kind of a multiplet kind of centered right around 7, and it integrates to 5 hydrogens. Now, if we look at this methyl group here, this methyl group is actually 4 bonds away from this hydrogen here. So it's not, those hydrogens don't split, and we get a nice singlet here. And that nice singlet integrates to 3 protons. So when we have a monosubstituted benzene with something that's not very polar, we see that it gets a singlet peak and it doesn't split very much. Also, notice the shift on this right here. This methyl group, if it was just a methyl group on a hydrocarbon, it'd be way down here in 1. But because it's next to the benzene ring, that shifts it up. That extra electron density shifts it downfield. Okay, so what if we had an electronic drawing group on our benzene ring? How does that change our pattern? And that does it a lot because our bromine here, number 1, it has electrons on it. So those electrons can share with the pi cloud, but it's also inductively electron withdrawing, which means these hydrogens are going to get the brunt of its electronic effect. And what we see is they get shifted further downfield. And if we integrate that peak, it integrates to 2 protons. Now these are farther away, and so they're kind of split in the pattern, but they're not shifted very far. So they kind of overlap each other for a total of 3 peaks here. So those are kind of overlapping, we don't see them. So the more polar this bond gets, the greater the separation here is. But we still should see in a monosubstituted benzene some kind of 1-3 pattern, or it'll all kind of coalesce into a single bond, a single thing, giving you a 5. Okay, so those are monosubstituted benzenes. What if we disubstitute our benzene? Okay, when we disubstitute our benzenes, we have 3 unique patterns we want to look for. But I'm going to show you this one on first and show you why we have different patterns. Okay, so on this side we have an electronic drawing group, just like we saw before. It shifts the hydrogens closest to it further upfield. I'm sorry, further downfield, and the other ones are less shifted here. And we know that this non-polar carbon-carbon bond doesn't shift it very much at all. Okay, so what we see is in our benzene system, we have the hydrogens closest to the bromine being higher and integrating to 2. And because these are magnetically equivalent to each other, they give a single peak. And these are magnetically equivalent to each other, they give a single peak, but they're each close to 1, giving us a doublet of doublets. Okay. So we have this specific pattern for parabenzenes or 1,4 substituted benzenes. They give us this doublet of doublets. Okay. Now let's look at this chain down here. What should we see for this chain down here? We have 2 hydrogens here, and we have 3 hydrogens here. And the hydrogens on the benzene ring are too far away. That's 4 bonds away. So they're not going to split anything. So these 2 hydrogens are going to be split by these 3 hydrogens in blue. Come on, blue. It's going to, so these hydrogens are going to be split into a quartet and have 2 hydrogens on it. And we see that here. We see a quartet with 2 hydrogens for those 2. Now, if we go in and look at the last here, now for this last peak, we have these 3 magnetically equivalent hydrogens being split by these 2 hydrogens, giving us a triplet and giving us a total of 3 protons there. So if we blow those up, it's a perfect, nice 3-3-3-3-1-1 and a nice 2-1-2-1 patterns. So we see the nice pattern that we see there. So, but the unique part about this is because we have this half being magnetically equivalent and this half being magnetically equivalent, we get this pretty doublet of doublet peaks in the benzene ring range, which is the 7 to 8 ppms. All right, so that's para. Okay, well, that's the 1,4 substitution. But if it's substituted differently, we get a different pattern. Okay. And we're going to learn a lot more about the benzene substitution patterns next semester, but I just want you to recognize that we did talk about the nomenclature of benzene in our chapter module 2. So the ortho meta pair should be part of our nomenclature. So you might have to review number 2. So let's look at the patterns when we have those different substitutions. So this is our 1,4 substitution. This is our 1,2 substitution, and this is our 1,3 substitution here. So like I said before, if we have a difference in electron withdrawing groups of the two groups here, we get this nice doublet of doublet peaks, always. The amount they shift changes depending on what the groups are, but we always get this doublet of doublets. Okay. Now, when we get something closer to this, where the 1,2 substitution, this one is very different than this one because of the fact of what they're nearby and what the inductive effect is there, okay? But then this one, these are about the same because they're far enough away to be not as. So what we typically end up with is 3 peaks in this ortho substitution, okay? Now, when we get to the 1,3 or meta substitution here, things go a little crazy because we have this hydrogen is different than all the rest. This hydrogen is different than all the rest because it's close to the nitro group. This hydrogen is different than all the rest because it's close to the methyl group. And this hydrogen is different than all the rest. And so some are being shifted and some are being split and some are splitting twice. And so what you get is this complex multiplet peak whenever we have this kind of substitution, because we really have 3, 4 non-equivalent hydrogens somewhere on there, each trying to split each other and shift different ways. And so we get this much more complex peak when we have this 1,3 or meta splitting pattern. All right, questions on benzene proton NMR? Come on, somebody's gonna have a question. Okay, well, now let's move on to our next type of NMR, which is carbon NMR. Now, carbon NMR actually turns out to be a little bit easier, okay? Now, there's 3 reasons carbon NMR are really easier. Okay, hydrogen was hydrogen 1, which only has 1 proton, which has half a spin, and is the primary isotope. Carbon 13, on the other hand, is only 1.1% of all of the carbons, okay? Which means you rarely get this carbon 13 and the carbon 13 splitting each other. So we don't have to worry about that, okay? Now, carbon 12 has an equal number of protons and neutrons, which means it has a spin of 0, and we don't see it at all in the NMR. So we don't see any of the carbon 12s, and we rarely see carbon 13 coupling, okay? The other cool thing is that carbon and hydrogen have different frequencies that they resonate at, which means we can take away all of the hydrogen coupling too. So that means we have no splitting. We have no splitting. So this is a great thing because if we have no splitting, that simplifies our material. So now all we have to do is worry about 2 things: the number of signals, and the number of signals is directly related to each type of carbon, not its position, each type of carbon. If they're chemically equivalent, they should have 1 signal in NMR, okay? And then the shift of those signals. And the shift of those signals is analogous to those in hydrogen. It's just shifted over a much broader range. So let's take a look at that. So remember, in proton NMR, most of our shifts happen between 0 to 10 ppm. And then we had that aldehyde and the carboxylic acid between 10 and 15. So that's the biggest band you would see would be 0 to 15 ppm. Okay, the carbon NMR actually splits out much higher. It's about 0 to 220, okay? And it's based on what's attached to it. And it's similar in the fact that if you add an electronegative atom, you add a halogen, you start adding carbonyls, they start shifting in the same amount relatively as we saw in the proton NMR. So our alkanes start here close to 0. And the cool thing is TMS is also our 0 for proton NMR and carbon NMR. So we know that we can use the same internal sampler for both experiments. And again, the more like methane you are, the closer you are to zero. Okay, so if you had methane, it's probably somewhere around 10 ppm. When you have only one hydrogen on that hydrocarbon, it's probably shifted closer to the 40. Okay. Now let's add an oxygen right here. That's going to shift it up to that 50 to 75. Remember, that's the first shift we see with both oxygen and or alcohols. We see those hydrogens shift up. When we add halogen, we get a shift most of the time up. Some halogens will shift it down. Iodine can occasionally shift it down, but it usually sees these shifts go higher. Having an oxygen next to a carbonyl, it actually helps shift it even higher, just above where we would see it for an ether or an alcohol. The actual carbons in the alkyne are shifted even higher, almost to 90 degree, almost to 90 ppm. Our alkenes are shifted higher to around there. Now there's a typo in my slide here. Benzene rings show up from 125 to 160. That's not 60, it should be 160. There's a typo there, sorry for that. And then carbonyls are usually the only things that happen above that. We can see carboxylic acid carbonyls below 200, but aldehydes and ketones are almost always above 200. So we see those same relative shifts we saw in the proton NMR in that same regime in the carbon NMR. So that the same deshielding rules of the substituent work for both carbon and proton NMR. Okay, so that means all we have to do is figure out unique carbons and what they're attached to try to figure out where things should shift. Okay, so based on that, just looking at it without even knowing anything, so this is most like methane, so that's going to be the furthest one up here, right? Then we have the one next to it here, but now we have this carbon right here attached directly to the chlorine. That's our biggest electron group. That's our biggest, electronegative atom. So we expect to see that furthest up from there. Okay. Then the next two are going to be, which one's going to be which? They're both one carbon away, but this one has 2 hydrogens on it, and this one has 3 hydrogens on it. So just from that kind of argument, we can say that this one's going to be the lower one, and this one's going to be the higher one. So the more hydrogens you are, the more closer to zero you are. The closer you are to an electronegative atom, the further downfield you're going to be. Okay, so you can predict these things just by looking at what are attached to the individual carbons. And because this molecule is unsymmetrical, each carbon has a unique signal. All right, let's see where we can shift everything up around here, okay? So we have the most like methane here, and then this would be the next most like methane because it's next to this carbonyl, this is next to a CH2, but that carbonyl is going to shift it up slightly. So we can tell the difference between these two because this is closest to a carbonyl and this is not next to any kind of thing. So we're going to get our 2 peaks down here identified. Now we have something bonded to an oxygen right here. That's going to be shifted up in that, the 40 to 60 range. So we expect to see that carbon that's bonded in this ester here. But now we have a carboxylic acid carbonyl. That carbonyl doesn't show up in proton NMR, but it does show up in carbon NMR. And so we can identify it because it's above this 160 range here. And again, it has this oxygen on it, which shifts it down here. If this was an aldehyde or a ketone, it would be above 200. All right, questions on the fact that we only have to have 2 things. We have to have shift and we have to have unique carbons. Okay, we're going to get a little more experience on that on Friday too. So what's really cool is in the carbon NMR, we can do what was called a depth experiment. And the depth experiment is looking for attached protons. And by changing the way we do the experiment and waiting different amounts of time, because they all relax at different rates, we can actually tell whether you have 1 hydrogen on your carbon, 2 hydrogens on your carbon, or 3 hydrogens on your carbon. And the whole reason is that when you have 3 hydrogens on your carbon, it relaxes faster than 2 hydrogens that relax faster than 1 hydrogen. And then if you don't have any hydrogens at all, you actually don't get a signal. Okay, so what we can look for in a depth experiment, and this is just for your, there we go, we're on the depth experiment. Okay, what we can see on a depth experiment is when we combine, this is just our regular NMR, the carbon NMR we should see. And we have 1, 2, 3, 4, 5, 6, 7 peaks right here. And then what we can do is by doing the depth here, we can see which peaks only have CHs on it. That helps us. That tells us that we have this peak here and that one there. We can identify those where they are. Number one, by shift, because E and B, the E is going to be here and the B is going to be here because this is on an oxygen and this is on a ethylene group here. But those are the only two with a single hydrogen on it. So we can easily identify those. Okay. Now, if we look at the second one here, carbons that had no hydrogens on it don't show up on the depth experiment very much at all. So that means this peak right here, this F right here, shows up in that one here as this little teeny peak because it didn't have any hydrogens on it. But notice this, these 3 peaks all have methyl groups on it. So that means those must be A, G, and H. And these 2 had just CH2s on it. So those must be the only 2 CH2s we have, which are C and D. So it's kind of a cool experiment. We don't use it as much as we do in this class, but once we get into spectroscopy and other classes, this is a very valuable experiment that kind of combines knowing what carbon NMR is, plus knowing how many hydrogens are attached to it. All right, questions on that? Okay, so our activity on Friday will be, we're gonna go ahead and do about 20 minutes on mass spec, and then we're gonna do an activity on proton and carbon NMR. The 3 things we're gonna be looking for there are looking for spin-spin coupling, looking for unique things, and getting a relative idea of shift just based on what things are chemically bound to them. Okay, any questions? Have you started looking at homework yet? It's good.
Yeah, I have a question. Will there be mass spec on the group activity?
Not on the group activity, no.
Okay.
They'll have just gone over it.
Right, okay.
Okay. So, all right, go and look at your relative shifts by what are attached to them and start figuring out what equivalent protons are and start figuring out what unique carbons are, okay? And then we'll drive it home on Friday. All right, I'm gonna go ahead and stop recording. If you wanna hang back and ask a question, go ahead. Otherwise, look for this online in about 30 minutes.